Ever start to think about how we make sense of the world? Like, how do we know what to expect, what decisions to make?
I'd say a good chunk of it comes down to logic, right?
Exactly. But today, we're going deeper. We're diving into the world of model logic, a way to formalize logic,
Hmm.
especially for complex systems. Think computers, algorithms, that kind of thing.
Ah, so not just whether I need an umbrella today, but how can we be sure that self-driving car doesn't run a red light?
You got it. And to help us untangle this, we've got a real expert in the field ready to jump in.
Absolutely. Let's unravel this.
So, model logic, where do we even start? What makes it different from just, like, regular logic?
Well, imagine you're not just dealing with true or false, but the meaning of the statements within a very specific context.
Okay, so context matters.
Hugely. It's like building a mini universe with its own rules. We call this intentional logic.
Intentional logic. So the words intentions actually matter.
Precisely. For example, in this mini universe, we might say having wings necessarily means you can fly. But in the real world, well, penguins have wings.
But they waddle.
Yeah.
Okay, I'm getting it.
Yep.
So it's about defining those relationships precisely, right?
Exactly. And we use special operators to do this, like necessarily, as we just said, meaning it always holds true.
And I'm guessing there's a counterpart for when things might be true.
Spot on. That's where possibly comes in. Think of it like the sun necessarily rises in the east versus it's possible I'll win the lottery today.
Okay, so it's not just about true or false, but different levels of certainty, all within this specific set of rules we're building.
You've got it. It's like creating a logical framework for a system to operate within. And this is where things get really interesting when we talk about temporal logic.
Temporal logic, is that time travel for logic or something?
Not quite time travel, but we are talking about how time affects truth. What's true now impacts what can be true in the future.
Ooh, like a chain of events.
Yeah,
Each one leading to the next.
exactly. Think of it like a timeline. Each point on that timeline represents a moment in time. And we can use temporal logic to express how the truth of a statement at one point influences the truth of statements at later points.
So if a program starts with a bug, it's likely to keep causing problems down the line.
Exactly. The initial state matters. And that's a key idea behind temporal logic. The past can influence the present and the future. This is crucial in designing things like software, where you want to ensure everything works correctly over time.
Makes sense. So we've got our mini universe, our rules, and now this idea of time influencing truth. What's next?
Now let's talk about actions and their consequences. What happens when we do something within a system? That's where mu calculus comes in.
Mu calculus. Sounds intense.
It's a mouthful, but it's really about cause and effect. Imagine you're driving a car.
Okay, I'm picturing it.
In mu calculus, we might say that pressing the gas pedal must lead to the car accelerating. We represent this as ARA phi. A cubri always leads to property phi.
So the gas pedal is A and phi is the car speeding up.
You've got it. But here's the thing. Not all actions have guaranteed outcomes.
Oh, right, like saving a file on my computer. Sometimes it works, sometimes blue screen of death.
Exactly. That's where we'd use A.phi. It means there's at least one case where action A leads to property phi, but it's not guaranteed. So clicking save might work, but there's a chance it won't.
So mu calculus helps us map out all these actions and consequences within a system, making sure things work as expected, or at least understanding what might go wrong.
Precisely. And it gets even more powerful when we bring in two special concepts, mu and nu. We use Greek letters and yi to represent these.
Greek letters. Okay, you're losing me a little bit.
Think of it this way. Imagine you're trying to find your way out of a maze. Mu, or a 1, represents the idea that you will eventually find the exit if you keep searching.
Okay, so you're guaranteed to get there eventually. But the maze could be really complex and it might take a long time.
Exactly. Now imagine a program that needs to run continuously without crashing. That's where nu comes in. It represents a property that must hold true along an infinite path.
So mu is about eventually reaching a specific goal, while nu is about maintaining a certain state indefinitely. Like mu gets you to the finish line and nu makes sure you keep running.
A great way to put it. And these concepts are super helpful in solving complex problems in computer science, like preventing those dreaded deadlock situations.
Deadlock, that sounds bad.
It can be. It's when a system gets stuck because of conflicting actions. Imagine two programs both needing the same resource to continue.
So they're both stuck waiting for the other one.
Exactly. And that's where these concepts of mu and nu become crucial in designing systems that can avoid these situations.
So we've gone from talking about the meaning of words to preventing computer crashes. It's fascinating how these seemingly abstract logic concepts have very real-world implications.
Absolutely. Logic is the backbone of so much in our technological world. And, it's not just about computers and software. Think about our own lives, our choices, the consequences, those what-if moments. Don't you see necessarily and possibly playing out every day?
That's a really interesting thought. Every decision we make is based on some kind of logic, even if we don't realize it. Whether we're aware of it or not, we're constantly weighing possibilities and trying to figure out the most likely outcome.
Precisely. And that's what's so fascinating about logic. It underpins so much of how we understand and interact with the world around us.
Well, you've definitely given us a lot to think about. This has been a pretty wild ride, from the meaning of words to making sure computers don't crash.
There's always more to explore.
Absolutely. So if this deep dive into model logic has piqued your interest, don't stop here. Go down that rabbit hole. Do some research on model checking, temporal logic, or just take a moment to appreciate the role logic plays in your own life. It's a fascinating world out there, and we encourage you to explore it.